Okay, welcome again to our lesson, Darasa Online. I'm Cyprian Mgina. Today we are going to study physics to the topic of electromagnetism. Basically, we'll be looking onto what we call self-inductance. That's where we're just going to concentrate. And we'll just be able to look even various applications of an inductor in an electrical systems. First of all, we need to know what do we mean when we talk when we talk about self-inductance. The self-inductance happens in this way that whenever we have a coil and the current is just flowing through that particular coil, the variation of a current which is flowing through that particular coil will generate a magnetic field. That magnetic field, whenever it interacts another part of the same coil, there is produced an induced EMF. And according to the Lenz's law, that induced EMF will be flowing in an opposite direction, trying to oppose the actual current which is just flowing through that particular inductor. And this particular EMF, which is produced within the same coil due to the variation of the current which is flowing through the same coil, this is called self-induced EMF. And because it's flowing in an opposite direction, sometimes we could be able to call that it produces what we call a back EMF. And therefore, from the Lenz's law, this back EMF, or the self-induced EMF, actually will be resisting the growth of the current which is really produced or which is really flowing within the same coil. And that particular coil, which can be able to show all of this particular property together with storing some energy, because there will be some magnetic field created within such a particular conductor, then that is what we call an inductor. And this inductor, as long as it is capable to store some energy, and therefore it can just be used in some particular electrical appliances, some transmitters, TVs, radios, and some other more electrical appliance, because it can just be used together with the resistor to time as a timer. Okay, as a timer. Whenever I'm talking about a timer, then you can just be able to know that there are so many uses of timing devices in an electrical systems. So basically, we need now just to start, because I believe you have already learned this. So more or less, we'll just be doing like a revision. I want to be able to go basically for the derivation of this particular expression from the first principle of what we have just learned in physics. So what we really need to know here we are talking about self-induced EMF. We are going to look what we call the self-induced EMF. The self-induced EMF is the one which is really happening in that particular inductor whenever a current flowing through an inductor is made to vary. So the EMF which is going to be induced within the same coil or within the same conductor produces what we call the self-induced EMF, or what we call the back EMF. And as I've already said, that this back EMF produces the growth of the current which is flowing through that particular inductor. Okay, the magnetic flux which will just be produced within an inductor, actually, as we have already looked into a Faraday's law, actually should be proportional to the current which can just be produced. So we are saying that if we talk about the coil having some particular number of turns, then the total magnetic flux, that is N phi, this should be proportional with the current I, which can just be induced into that particular coil having an N number of turns. So if I'm going to remove the proportionality sign here, then I'm just going to have an N phi to be equal to a proportionality constant L times the current I. Now the proportionality constant L, then this is what we call an inductance of that particular inductor. This is what we call an inductance of that particular inductor. And as what you have already seen from the Faraday's law, we had said that the EMF E produced in the rate of change of the magnetic flux is proportional to, the induced EMF is proportional to the rate of change of the flux. That from the Faraday's law, we are saying that E is just equal to minus, the rate change of the magnetic flux. The rate change of the magnetic flux, just like that one. And you could just be able to find that if here I'm talking about the induced EMF E, then any phi here could just be the same as the product of an L times I, an inductance of an inductor times I. So you can just be able to find that we could also again be able to say that the EMF, the induced EMF E, will just be equal to the rate change of L times I. So we are having these two particular expressions. The EMF which is really induced in that particular inductor, as we have already said previously, that it opposes the growth of the current in a circuit. So it means that there must be a work which has to be done against this, the opposition of the self-induced EMF within a circuit. So that particular work done, actually, that particular work done should just be equal to due to the self-induced EMF in that particular circuit, at which it have just to which will be opposing the growth of the current will be given by that particular expression. And therefore, you'll just be able to find that if that is the case, we'll just eventually go on with that particular derivation until we'll just be able to get the actual energy. And I believe we have already derived this previously because here we're just doing a revision. Actually, you'll end up having that particular work done will end up having an integral from 0 to time t for an Li di dt with a negative sign, because here we are talking about that particular back EMF. We are talking about that particular back EMF. And for that case, we will just be able to find that as we derive the whole of this particular expression, we will end up having the total work done. The total work done, which actually, the total work done as we derive this from the time 0, the initial current of the back EMF was 0, and at the time t, the actual back EMF could just be equal to I naught, and therefore L being a constant can be taken outside, and you will eventually be getting as a half times I naught squared, being the energy which is stored in an inductor. The total work done, which is equal to the energy which is stored in an inductor. Okay, that particular work done against the back EMF, it is Li di dt. No, sorry, it's not dt. It is just Li di, such that on the process of doing an integration from time 0 at the boundary condition to the last time t, the total work done will just be equal to a half times L times I naught being the maximum equilibrium current that is flowing in a circuit, whereby that particular work done, this particular work done actually is the energy. This is the energy that is stored in an inductor and which is measured in joules. So this is the actual derivation. But actually, whenever we are talking about the self-induced EMF, we are really talking about an inductor being connected to a resistor, so that we could just be able to use an inductor successfully, because an inductor by itself won't be very successful unless it's just being connected to a resistor, whether in series or in parallel. And that particular circuit is just like this one, which I'm just going to draw it to you. And the whole process of the self-induced EMF can happen, just as I've already mentioned previously, in the way that such an inductor now can just be used as a timer for some particular electrical appliance, just like transmitters, TVs, whatever. So we could have such a simple circuit of a resistor there and an inductor there, connected to a battery there. And we could have we could have a switch here S connected at A and connected at B there. Then this can just be a resistor and this is an inductor. And this could just be producing a battery producing a certain EMF E. So the first case, whenever a switch S is connected to B, there will be a current which will be flowing through the circuit. And that current will be depending upon the battery E there. And this can go on while that particular current goes or is just produced in that way. There will be another back EMF which will be produced within an inductor, just trying to oppose this. So in a particular given time, the growth of this current won't go on indefinitely. It will come to a moment where that particular current will reach a maximum. So that we could now just disconnect the switch S from B to A. And then we could just be having a circuit containing an inductor and a resistor only. A resistor and an inductor only. And the only current which will be flowing at this case will just be the current due to the self-induced EMF. Will be the current due to the self-induced EMF which will just be flowing through a resistor. And this current can now just be decaying from an initial value to a particular value. There is what we call an exponential decay. The growth of the current at the first part was also exponential. As well as whenever it decays, there is what we call an exponential decay. And we can just be able to see these particular equations. I believe you really know on how we have just derived, whereby we could just be able to obtain what we call an inductive time constant, the time at which a current, the growth of the current in an inductor depends on to reach to a particular value whenever we are having such an exponential growth or an exponential decay of a current through an inductor. Now the current which will be flowing through an inductor, as we have already seen into the first circuit, that once a switch is closed, at A and B, whenever the switch is closed at A, it means that here we are taking a resistor and this to be an inductor. The current which will just be, first of all, we are looking whenever the switch S is closed, let's say at B. Okay, we close it at A, and then there will be some magnetic field and some energy stored in an inductor, such that whenever a switch is closed at B, then we'll just be able to find that the actual current, the actual final current I will just be equal to I naught E into RT over L. So we'll end up having that particular expression. But whenever you take the switch S, you connect it to A, it means that there will be a current which will just be flowing through the circuit. And such that that particular current I will be opposed due to an EMF produced by an inductor L. That the resultant current I actually just be equal to I naught minus I. Okay, and for that case, we are having the I naught minus I. It is I naught there, which is I naught E into minus RT over L. And if I take I naught outside, instead I'll be having 1 minus E power minus RT over L, an inductor. And we'll end up having this to be I naught into 1 minus E power minus T over L over R. Okay, we are having that particular expression. This is the main current I, which will be flowing through in the circuit. But the L over R, this is what we call tau, and this is called an inductive time constant. This is what we call an inductive time constant. An inductive time constant, which can be able to project at what time will the current be of a certain magnitude. So we are having a general expression as it is given by this particular equation here. And then from this particular expression, we can as well be able to see how we could just be able to solve various problems with regard to an inductor and be able to project or to determine at what particular time will the current, let's say, for example, be a half of the initial current flowing through that particular circuit. So depending upon the question, we can just be able to go and see some various questions which are really very challenging to you, and I hope through that particular question that will just take us to a new level of solving those particular problems. Okay, students, let's go to our first question. Our first question goes like this. A coil with an inductance of 25 Henry and a resistance of 15 ohms is connected in a series with a battery of EM of 12 volts and a switch. Determine the following. The rate of change of the current immediately after closing the switch. B, find the final current. C, find the current in the circuit after 4 seconds. D, how long does it take for the current to grow up to 0.45 ampere? So here we are given a coil of that particular inductance. So our coil have an inductance of 25 Henry, and the resistance there is given to be equal to 15 ohms, and this is connected to a cell of an EMF 12 volt, okay, with a switch. So to determine the rate of change of the current immediately after closing the switch, really here you have to know that here we are talking about our inductor, we are talking our inductor there and a resistor there, connected it to a battery there. So this could be a resistor, this could be an inductor, and this could be a battery producing an EMF of that way. So from the Kirchhoff's law, whenever we want to determine the rate of change of the current immediately after the closing the switch, then we need to look from the Kirchhoff's law of this particular circuit, that E, then this is equal to L di dt. The whole of this is just equal to IR. Remember, we are having negative sign because of the back EMF which is flowing through the circuit. But immediately after closing the switch, there is no current which is just flowing there. So we'll just be having E minus L di dt to be equal to 0. And our interest is to define the rate change of the current. And if that is the case, this will just be equal to E is equal to L di dt. And we substitute for E, the value for E, this is 12 volt. And L, this is 25 Henry. So we are having this to be equal to di dt. So di dt, which is the rate change of the current, this will be equal to 12 over 25. And if you compute there, you will just be able to obtain, 0.48. 0.48 ampere per second. So this is the rate change of current immediately after closing the switch. Let's go to part B. We are looking the final current. The final current is just obtained this way, that particular current I, just from the Ohm's law, we are taking this to be equal to E over R. E being the EMF, the voltage for the battery, which is equal to 12, and the resistance is just 15. So I'm just going to get the final current will just be equal to 12 over 15. That is, using your calculator, you take 12 over 15, this will be equal to 0.8. So that is B. That is the final current. Okay, part C, we are going to look at the current in the circuit after 4 seconds. So the current in the circuit after 4 seconds, it takes us from that particular equation. I is equal to I naught into 1 minus E over R T over L to that much. But I naught there is just equal to E over R. Okay? So this will just be equal to the current I 1 minus RT over L. So it's a matter of substituting to obtain the current I at the moment the time is 4 seconds. So that if we substitute that particular value, then we'll just be getting something like this. That is, we are looking for a current I. The value for E, that is 12 over R, that is 15, into 1 minus E power minus R. The R, that is 15 ohms. And the time there is 4 seconds, so we multiply by 4 seconds over L, and our L, that is 25 Henry. So we just have to compute for that. So if we compute for that, we are having 12 divided by 15. This is 0.8. Into 1 minus E power minus 15 times 4, that is 60. So we divide by 25, we getting 2.4. And then we can be able to compute to find the final current after 4 seconds. And we can be able to proceed here. So this will be 0.8 into 1 minus E power minus 2.4. This is 0.0907. 0.0907179. Proceed it over there, and we'll be getting 0.8 times that much, 1 minus that. We'll be getting 0.90928. And our last answer, then if we multiply it to 0.8, so we'll be getting 0.72742, etc. Up to the third decimal place, the current I will be equal to this much ampere. This is the current in the circuit after 4 seconds. Then that is after this particular 4 seconds. This will just be the current to be flowing in that particular circuit. To part D, the last part. How long does it take for the current to grow up to 0.45 ampere? How long does it take for the current to grow up to 0.45 ampere? So really, it takes us to the same expression as that one for part C. So here we need to determine the time t for the current to grow up to 0.45. So the current now will just be equal, this is part D. So the current will be equal to 0.45, and this will just be equal to E over R. We substitute it there, and 1 minus E power minus RT over L. So we substitute the values now, and we need to determine the value for t. So that if we substitute it there, the value for E, that is 12 volts, the R, that is 15, and this will be equal to 1 minus E power minus R. R is 15. That will be equal to 15 T over L, which is 25. So we compute and be able to determine what is the value for T. And as we could just be able to go here, we could just be able to find that this will be equal to 12 over 15. This will be equal to 0.8. into 1 minus E, and that is 15 over 25. This is 0.6T, and this is equal to 0.45. And you could just be able to find that from there, I can take 0.45 divided by 0.8. I'm going to get 0.5625 to be equal to 1 minus E power minus 0.6T. And then we are solving for that E power 0.6T. This will just be equal to 1 minus this much, 0.5625, which actually is equal to 0.4375. So if I'm taking ln to both sides, 0.6T, this is equal to ln 0.4375. This is minus 0.8266, and the ln of this is equal to minus 0.6T. So the value for T will just be equal to 0.8266 divided by 0.6. So if we take that, we divide it by 0.6, this is equal to 1.377 seconds. So the time, it will take 1.378 seconds for the current to grow up to be 0.45 ampere. So this is for part D. This is for part D. Okay, students, let us now go to do the question number 2. The question says, an inductor of 3 Henry is connected in series to 10 ohm resistor and a switch. These devices are then connected across a 3-volt battery. When the switch is closed, the current starts to flow immediately in the circuit. And after 0.3 seconds, which is one inductive time constant, determine the following. A, the rate at which the energy is being delivered by the battery. B, the rate at which energy appears as joule heat in the resistor. And C, the last part, the rate at which energy is being stored in the magnetic field. That is the magnetic field of an inductor. This is the question, and we can be able to solve this the way you can just be able to follow me. So with this question, we are using the same with the same expression. The same expression that the current I is just equal to I naught into 1 minus E power minus RT over L. This is our basic equation, where the I naught there is just equal to E over R into 1 into E minus RT over L. But what we have already said previously, that if I take E over R, which is equal to 1 minus E, now there I'm just going to get minus T over tau, an inductive time constant, where tau there is just equal to L over R. Now we have been asked to determine now the rate. If we are starting, let's say, with part A, we are going to determine the rate at which the energy is being delivered, the energy that is being delivered by the battery. So the rate at which the energy is being delivered by the battery, at the first case, you need to determine the current. So we just have to determine the current I. So determining the current I, we need to know about the values of E, the values of R, and the value for the inductive time constant. But the inductive time constant, we had been given that is equal to 1 inductive time constant. So the whole of this much, this should just be equal to the time t, of which will just be equal to 1. And therefore, if we substitute the value for E from the equation which is given there, that is 3 volt, and the R, that is 10. So we shall be getting 3 over 10 into 1 minus E power minus 1. And from there we can be able to compute to obtain what is the current I. And this will just be equal to 0.3 and be equal to 1 minus E power minus 1. And we can be able to compute this to obtain what will just be the value for the current, I. Using the calculator, you'll be able to find that this will just be equal to 0.3. Here we are taking 1 times 1 minus E power 1. So if we're just going to look for the value of, for the values of E, will be equal to that one. I'm computing for this value here. This will just be equal to 0. This will just be equal to 0.63212 using your calculator. And therefore, the current I, if you compute, you will just have to multiply by 0.3, and you get 0.1896 amperes. So this is the current which is flowing in a circuit. Now to determine the power, you need to multiply the current I times the voltage. You need to multiply the current I times the voltage. And the rate at which the energy is being delivered to the battery, that is the power. Then you have to multiply current times the voltage. The current is given there, which is 0.1896 times the voltage. That is where the battery had been connected to. The voltage is 3 volts, so we multiply by 3 volts. That's the voltage of the battery. And then if you multiply by that much, you will be getting 0.56. So the power there will just be equal to 0.5689 watts. Or rather take to be 0.6 watts. So this is the rate at which the energy is being delivered by the battery. Okay, again, we proceed to our second part, that is part B. We need to determine the rate at which the energy appears as joule heat in the resistor. The rate at which the energy appears as joule heat in the resistor. This is also a power. And if we go very, very quickly to this particular expression, you'll just be able to find that as long as we are talking about as long as we talk about the power, then as long as we have already obtained the current I, then this will just be equal to the current squared times R. So that we can be able to substitute. We have already obtained the current, which is 0.56, which is 0.5689. 0.5689, we multiply, so this is the current, we square this times the resistor. The resistor there connected is 10 ohms. So we just multiply there and be able to get the power in watts. So if we multiply there, then we could just be able to get the answer there. So the answer, that will just be equal to 0.3236 watts. So this is the rate at which the energy appears as joule heat in the resistor. This is part B. Okay, let's go to part C. We need to determine the rate at which the energy is being stored in the magnetic field. This energy, which is being stored into the magnetic field, needs us to go back to our basic equation, which is this one there. And I can write it again here. That particular equation, I is equal to I naught, which is equal to E over R, into 1 minus E power RT over L. So we need to determine the rate change of the current. So the rate change of the current, this is equal to di dt. So differentiating this with respect to time t, here we are going to get E over R times the derivative of this with respect to t. This will be equal to R over L, E power minus RT over L. So we're having that particular expression. But remember the inductive time constant, which is equal to L over R. This is just equal to 1. Okay, this is just equal to 1. That particular time t is just equal to the inductive time constant. 1 inductive time constant. So for that case, the whole of this much, the time t is just equal to that much, then we could just be able to have the di dt will just be equal to E over R, R over L. This and this will cancel, shall be remaining with E over L, and this will be equal to E, will be equal to E power minus, will be equal to E power minus 1, will be equal to E power minus 1. And therefore, we just have to substitute. We just have to substitute for these values to obtain the di dt. Substituting for those particular values, we know the value for E, which is just equal to 3 volts. The value for E, which is just equal to 3 volts. And an inductor there is of 3 Henry. So we multiply with E power minus 1 of that much. So we can go with our calculator and be able to multiply there. So we are going to get 0.3678. This is the I dt. So having obtained the rate at which this this is the rate change of the current. This is the rate change of the current, and this will help us to obtain our last question. Okay, let's just proceed. Let us proceed with our part. We have just looked at the rate, the I dt. Now this will help us to determine the energy that which will eventually take us to obtain the rate at which the energy is being stored in the magnetic field, that is of an inductor. So first of all, we need to know the energy which will be stored in that particular inductor. Let me put it L. This is just equal to du, the energy that is stored in an inductor. Let me call it U sub L dt. Actually, this is equal to Li di dt. And we can be able to obtain this. For an inductor, L is 3, and the current that is just crossing through an inductor, the current that is crossing through an inductor, we have just obtained in part A. This was in part A. This was 0.1896. This was 0.1896, and the I dt is this one which I've obtained here, which is 0.3678. So if we compute for all of this, if we multiply 0.3678 times 0.1896 times 3, we obtain 0.2092. This is the power that is That this is the power from an inductor. But from the conservation of energy, the total energy, actually, the total energy, which will now just be obtained into the, the total energy will just be equal to the total energy due to the energy which will just be stored in a resistor plus the energy which is stored in an inductor. Okay? So, to obtain now the answer, to obtain the rate at which the energy is being stored in the magnetic field, now it's a sum total of this power plus the power which we had just obtained earlier in part B. So that by the conservation of energy, the power which will be stored into the in the magnetic field, the rate at which energy is being stored in the magnetic field, which is power, this will just be equal to the rate at which the energy appears as joule heat in the resistor, which will just be equal to 0.359 plus this much, which we have already calculated here, to which is just equal to 0.2092. So if we add here, we're just going to get the total energy. So the total energy, if we add there, plus 0.3359, then we're just going to get 0.568. 0.568 watts. So this will just be the rate at which energy is being stored in the magnetic field. That is question number 2. Okay, students, having looked all of these questions, then I do hope you are now in a position where you can just be able to solve these particular questions, where you can be able to determine the current, the time, an inductive time constant, which is really originating from an inductor whenever it's just being connected with a resistor. And this will just be helpful for you, and it can enable you to take even to some more level of doing some more difficult questions. But as long as you understand the way we could be able to reach to those particular formulas, especially just like the one over there, and the way an inductor behaves whenever it's just been connected in a resistor, then I do hope you will be able to do those particular problems without any problem. And therefore, what we are going to proceed now, just after a short break, we'll just come back and be able to share with you some questions as a homework, and we'll just be able to see technicalities or how the questions can just be solved very comfortably. Once you just go about reading a question, you understand what is really demanding you to understand just before you embark solving that particular question. Then you can just be able to agree with me that all of that particular problem with regard to an inductor connected in a circuit will just be very easier for you to do it. So let's go for a short break. When you come back again, then I'll be able to share with you some few questions, and those will just be the questions for your homework, but I'll be able to give you some small hints for that. Okay, students. Now here we are having a question as a homework, but I'll be able to give you some hint. Question goes like this. A circuit contains a solenoid of inductance 60 Henry and a resistance of 40 ohms, which is connected to a switch and a 100-volt battery. The question says, how long will it take for the current to reach a half of its equilibrium value when the switch is closed? So that is the question. And really, we are having a circuit just like this, as what you have already done previously. So what you are supposed to look here is to determine the time. From the given equation, as it is given there, you need to look for that particular time t at which the current will be able to reach 1/2 of its equilibrium value. That the I naught here is the equilibrium value. And this equilibrium value should just be equal to a half of the, should just be equal to a half of should just be equal to a half of that much. That this value should be equal to a half of that much. So if you substitute this value to be equal to a half, as the I naught here is the equilibrium value, so if you take a half of it and substitute the values for the value for a resistor and for an inductor there, and all of the values here can just be computed, and you'll eventually just be able to obtain the time at which the current will just be able to reach at the moment the current reaches just a half of its equilibrium value. That's just a hint, and I hope through mathematics you can just be able to compute this and be able to do that particular question comfortably. Okay, let's go now to our homework number 2. It says the current in an RL circuit builds up to 1/3 of its steady state value in 5 seconds. What is the inductive time constant? And B, the inductance of a closed-packed coil of 400 turns is 8 millihenries. So what is the magnetic flux through the coil when the current is 5 times 10 to the negative 3 amperes? Okay, these are 2 distinct questions. The first question, as I'm giving you as you take it as a homework, remember this is the circuit that contains an inductor and a resistor. As we have already looked from our first model question we have just solved, you really need to refer that particular formula to determine an inductive time constant, which is equal to which really comes from that particular formula, L over R. And through that, you can just be able to compute and be able to obtain an inductive time constant. So the second part as well, we have been asked we have been given the inductance of a closed-packed coil of 400 turns is 8 millihenries. This is just like an inductor. Now we have been asked to determine the magnetic flux through that particular coil when that current, when the current which is just flowing through it is 5 times 10 to the negative 3. You can be able to refer those formulas. Part B. In this part, we are given a coil which works as an inductor, but it has 400 turns and it is of 8 millihenries. Now you have been asked to determine now the current. You have been to determine the magnetic flux. Whenever there is a certain current that is 5 times 10 to the negative 3 amperes just flowing in it, then I hope you can just be able to go and do it by just referring the previous formula which we have already used and derived in our previous case. Okay, students, it's very difficult to preempt all of the cases with regard to an energy stored in an inductor, but I do hope next time when we meet, we'll just be able to discuss even to some other areas of the problems which can just be very easier. As long as you know these particular formulas, it will just be very easy for you now just to follow and be able to solve those other problems, of which I believe they are challenging problems to you, but as long as you remember these particular formulas, you know how to derive, you all know about those particular formulas for the energy stored in an inductor, you will eventually be able to do those particular questions comfortably. Thank you and see you next time.